So our next talk is actually from very well known, Sujit Dey. So Sujit, if you'd like to come up, I think we're going to get your slides ready. But a couple of little known facts about Sujit is that he's really been a big proponent of energy efficiency and energy use for many years. And we've had several discussions about it. He was describing to me how he had at one point a project to work on renewable energy in base stations and how that was going. Clearly it was before it was sexy, Sujit, but he's also involved in a small company called Igren that I think does solar panels or solar power in different aspects of the network. We'll probably hear a little bit about that. Small at this point, but hey, from small things, big things grow. And we just heard excellently from Brian how, well, we'll talk about it in the panel session, but how generating energy at the point of use is probably the best, most efficient way to go. So Sujit, let me hand over to you, and thank you for joining us today.
Mark would not have a no for an answer. He asked that if I can give an overview of energy efficiency research in wireless. Now, as you know, that's a huge topic. And so I kept negotiating with him, and I said that, okay, let me try to represent all the research that is going on at UCSD. And then I quickly realized, especially after I committed to him, that that's also an impossible task because, there's just so much work that has been going on. So, I'll be honest, I started looking into this thing just, through all the madness of organizing this conference about a couple of days back and put together most of the slides yesterday. So the reason I'm saying all this is because I really left out so much. Now, just giving a very quick overview of the work that goes on at CWC. So the great thing about CWC is that not only is it vertically very deep, going from applications to wireless multimedia networks, physical layer, 5G, 6G circuits, radio architectures in between. But I would say that in almost every part of it, at every layer, there's a lot of research that goes on or has gone on in terms of power efficiency, energy efficiency. I see a lot of faculty sitting here who Gabriel is trying to say something, but maybe Gabriel, you can come up here and say. But I see Ramesh here, who has worked on at the network layer, for battery, for various aspects, sleep mode, all things energy for a long, long time. I see Peter Asbeck. I see people around here who have been working on at various levels. Unfortunately, as I said, that because of limited time, I could not pull the slides from them and sort of give a comprehensive overview as I might have been able to do, or maybe in some future. But as Mark said, as I was reflecting yesterday, I think many of us have spent a lot of time in our career thinking about power, looking at energy efficiency, looking at sustainability. And it's not that it was not sexy or not. That was never the point. NSF, various DoD has funded, very, very generously energy research for a long, long time. The problem always has been that who is to adopt these techniques and how. So energy always been, even from my days at NEC, we would do a chip design, and yes, power efficiency is good, but is it area efficient? Is it meeting the latency requirements? Those always were the first-class citizens. That was always the problem. So I just wanted to, as I was reflecting yesterday, my second most referenced paper I realized is on energy, battery-driven SoC systems. My IEEE fellowship is on low power design. As Mark said, I have a co-founder of a small company. We are focusing on EV battery technologies. So we have been, and I'm sure many of our faculty have been doing various things around energy efficiency and around sustainability. So I wanted to touch upon two things, and again, apologize because I was putting together everything last night. I still have maybe equations and things like that floating around. I didn't want to have them in my slides, but I have not been able to eliminate all of them. But I'm going to look at a conceptual level, the various approaches me and various other researchers have been working on. And I'm going to focus on just wireless networks and on RAN more specifically. So there are two aspects, right? One is energy efficiency, the other is sustainable communications. They are not the same. So for instance, you can make anything sustainable computing, sustainable communications, which actually requires much more energy. But in using renewable energy, you may end up spending a lot more energy, but you are trying to reduce the other kind of energy resources, right? The fossil fuel kind of energy. So there's a big distinction between the two. So one of the techniques that us and many other researchers worked on several years back, and again, this was generously funded by NSF. So again, always happy that funding was never an issue for all these work. The concept is very clear. Like, I think that Mark or one of you mentioned that the best form of power savings is shutting down. But that cannot be always possible. So on the left-hand side, what I'm showing is an example where there are some video users, some voice users, and there are some base stations which are covering the users, right? The users are associated with some base stations. And mind you that each of us at any given time are associated with many base stations. So in this a simple picture, what we can do, and we are showing on the right, is that we are zooming some cells. We are increasing the coverage of some cells and actually reducing the coverage of some cells, shrinking some cells. And in the process, we are eliminating E in the sense that E doesn't need to be up for some time. So we are not shutting off all the base stations. We are shutting off E, but by shrinking and zooming some of the other cells. So we came up with techniques. We called it dynamic network planner. So network planning is done. Those of you who have worked with operators, they go and scope out, and try to predict what kind of traffic will be there. I have worked with multiple operators when I had my company Autiva Wireless, and I learned from them how they're doing network planning, and then I just introduced a dynamic aspect. The dynamic aspect is about where the load is always changing. Those days when we were doing the work, there was no machine learning. We didn't use machine learning. We didn't use predictive. So we used all heuristic algorithms, seeing how the load changes and the QoS changes, QoS demand changes. Can we effectuate, base station selection coupled with power adaptation? So each of the base stations, the power can be adapted, and then user association. Because, for instance, if you look at the left-hand side example, the users associated with E were distributed to with E were distributed to A and D. So we came up with algorithms. We called it the bundle dynamic network planning, which can essentially look at the users and their QoS requirements at any given time. I think if I remember correctly, in about a second time we effectuated it every second, and essentially do what I'm showing on the left-hand side. Again, not going to algorithms or anything like that, but this is on the left-hand side, and I think that I can say now, we were not allowed to say at that time when we were publishing, but this profile is from T-Mobile. It's a base station utilization profile where we were also given the base station users, their what kind of rate requirements and all those things. And if we had all the base stations active, the power consumption, or I would say the energy consumption, would have been 337 kilowatts hour over 2 days. Whereas if we had adapted the base stations, some are getting on and off, depending, based on our algorithms, then we actually cut down by about 45%. And if we do further, that is, if we are also adapting the transmit power level, then we can shave off another maybe 7-8%. So this was very encouraging. And then what we thought was, well, why not drill down into the base station? So if we get into the base station, then we have three things we can play with. One is that how many RF chains we are making active at any given time. So the base station is active. It's not put on sleep. But we can play with how many RF chains are active. And for each RF chain, we can play with how many frequency slots and how many time slots we are utilizing. So in an all-on situation, everything can be on, and depending upon the scheduling algorithm, it's not energy aware. It's figuring out what frequency slots, what time slots are occupied, and all the RF chains are available. Whereas in this dynamic RF chain switching, we are essentially for every time frame, we are deciding how many RF chains are active and what frequency slots and time slots are active. And using that, again, as you see, and again, not going to the algorithm, but we can save, for the same profile, we can save significantly. If all the RF chains of an active base station are active, then the red is a profile of the RF chain power consumption, and this is what it is over 2 days for the total base station power consumption. Whereas if we are using our algorithm, this what we call the dynamic RF chain switching algorithm, then we can significantly reduce, as you see, the green flat waves. And the savings is also shown. Of course, for the RF chains themselves, the saving is significant. For total base station power consumption, proportionately, depending upon how the base station is modeled, the overall power consumption reduction goes down, but it's still very significant. Now, you may wonder that how did we simulate all this, right? So the base station power modeling is a topic which has been active for a long time. And while we did work with our industry partners to get some numbers here and there, but we could never really work on a particular base station. So we had to adapt to power models that are available, base station power models that are available. Also, LTE advanced working group had various specifications and so on, and all of those things we put into a MATLAB simulation environment. And also, if you noticed that from the previous slide, it was not only one base station, but it was across multiple base stations, right? Because in a coverage area, you have various base stations. We extended all this work to what is called cooperative base stations. I'm not going to go over all of those things because then it will become too many slides. But switching to something else and going even deeper, so I started at the network level and I'm going deeper and deeper. We started thinking that when massive MIMO was on the horizon, then some people were very happy that there'll be much better energy efficiency, right? Per bit efficiency was much better. However, we observed that the overall power consumption is just increasing more and more. So we talked to a whole lot of experts and we adopted what we call hybrid beamforming. So essentially these hybrid architectures, the number of RF chains and the number of antennas do not have to be the same. They can be, the number of RF chains can be less than the number of antennas. And so our approach, and I'm looking, I'm sort of trying to describe the approaches. Our approach was, can we look at what is the distribution of users and what is the QoS requirement as reflected by the bit rate, the reliability, and so on, and figure out dynamically which RF chains will we have on or not. So let's say a particular configuration, massive MIMO configuration, has 64 antennas and 32 RF chains. Well, sometimes we'll keep all the 32 RF chains active, and sometimes we'll power down some of those. So that was our goal. And we quickly realized that, so if you look at this, and I know it's kind of complicated, but so we are switching the RF chains every 1 second. That is, we are determining every 1 second how many RF chains will be active. So MT means the number of RF chains active. What you see here is if we have 64 RF chains active, then we are always at every, and these are called where the beamforming scheme is being changed. So within this 1 second, we have the beamforming scheme changing all the time, okay, every millisecond. And what we are showing in red is when the QoS could not be met, that is the data rate, maybe the reliability could not be met. And so as the number of RF chains are reducing for the same number of antennas for a certain distribution of users, you see more and more red, right? Now the question is that depending upon the users and the QoS requirements, can we quickly try to determine what is this best number? What is the best number for this particular scenario so that we can figure out a power so that we can figure out the number of RF chains with least power consumption and with least power outage probability. Now, we analyze this problem. It's an NP-hard problem. And so, we could have come up with heuristic algorithms, but now we are in the era of machine learning. So we thought that, okay, why not use machine learning? Why work hard and come up with heuristic algorithms, right? So what we did was we spent quite some time gathering a lot of data. So on the left, you'll see is we had various kinds of rate requirements, channel gains, outage probability requirements, maximum transmit power, bandwidth, and so on. And we simulated whole bunch and came up with training data. And based on that training data, we came up with essentially a machine learning model. And I'm sorry, I'm skipping all the details. And then online step was, given a particular scenario, then can we use that machine learning model to predict or to tell us what is that number of antennas to use for this particular hybrid beamformer. And going through all the, sort of getting over all the details, the results were quite promising. One of the things that we those days, and I'm talking of, I think, 4 or 5 years back, yes, 5G was coming, and yet talking to various standards, people working in standards groups, and I'm definitely not one of them, the hooks were still far and in between. It was difficult to sort of effectuate these things in the network. But what I'm hopeful is that with 6G, that many of these things, and we are not the only research group, there are many, many other research groups who have been working on these things, that the 6G working groups hopefully will listen to what that academic research has been and sort of see how some of these techniques can be incorporated. I'll just quickly touch upon, if I can get 2 minutes, on this sustainability aspect. One of the biggest challenges of using renewable energy for wireless communications, and I'm sure it's for many other sectors, but for wireless communications we found, we discovered so there are a lot of solar panels, as you know, around UCSD and a lot of base stations. So we did measurements. And we saw 2 interesting things. One is that the solar power generated and also the wind power generated is extremely fluctuating temporally as well as spatially. And so is the base station power consumption, though it's not as much. So one of the NSF funded projects that we did was that how can we close the gap between the surplus, so solar power and wind power, there is sometimes surplus and there is sometimes deficit, right? So what I'm showing here is if I send a YouTube video across, and this time, I think this was over a 4G network, and we are measuring how much is the power generated in green and how much is the power consumed. And you see that sometimes you unutilized surplus and sometimes deficit. So we came up with techniques. I mean, one of the ways of solving this problem is using batteries, right? So you store a lot of the unutilized solar power or wind power, but battery is expensive. And so we came up with techniques where when there is unutilized or surplus power, we send more data. And we rely on buffers, the network buffer, the device buffer, and so on. And when the power is less, then we can utilize that data. So that is a general technique that we created. And because my time is up, what I'll say is that we not only did simulation, we got more encouraged by the results and actually started building prototypes. And the thing, and NSF was very encouraging to us, the thing that they allowed us to do is to actually build a prototype and ask the question, can we have small cells which can be totally sustainable? And we quickly figured out that no, it cannot be done. But then the question became that, can we have the downtime lowest? So what is that combination of solar power, wind power, and battery that reduces the QS downtime of small cells? And so we did that for RSUs and solar. So RSU is a perfect small cell. And so with this RSU, we could figure out that for a large part, I would say, and we can give various quantification numbers, but I would say that if you can figure out the traffic, and if you can figure out the right battery size and the right solar panel size and so on, we saw in our various experiments that indeed we can operate the solar panels significantly well. Of course, if there are cloudy days, if there are snowy days, and so on. I mean, there are various contingencies, but all the results that we got were quite positive. And one of the things that I would love for, with this new interest in sustainability, is for the community to look more into it and see, because small cells and densification is to come, right? It's going to be staying with us. There's going to be much more densification within our buildings and so on. And I think that one of the important things we should look at is that how can we have zero net power consumption, and also remember the carbon footprint. So how can we reduce carbon footprint, and by doing two things. One is that, of course, designing these cells in the right way, so that they are utilizing solar power as much, and also balancing their peak hours, the peak shaving that is already instituted by utility companies. Can we bring in those concepts here? And the second thing is that can we have the behavior of the users also change? And that has been also done in various other sectors. Can we do that for instance, in the nighttime? Of course, we'll not shut off our phones and we'll not shut off using those, but can we institute policies which encourages more, like, I'm talking of gamifications, I'm talking of rewards, I'm talking of more cost, that can, have us do more work or use these small cells much more when there is much more renewable energy. So I would like the community to look into those policy aspects also. Thank you.